everyone, thanks for joining this session. My name is Piotr and I am one of the managers in Nvidia Warsaw office. My work is around deep learning for tabular data and graph neural networks, and today I will be talking about graph generators that can efficiently generate graphs that can be later used in many applications, including simulating performance of GNNs. And as the topic is broad, please forgive me the fact that for some of the issues that I will present, I will just mention them without full elaboration. Okay, so the topics that I will speak about today are, first of all, why do we even need a synthetic data generation for the graph neural networks, and what are the properties of ideal generator? I will show you one of the most common generators and the modifications one needs to apply to make it an almost perfect graph generator for the graph neural networks. How to fit that generator's parameters, because it's not that obvious. And then I will spend a couple of minutes on the results. That is, what can we get in terms of the graph characteristics and mimicking the performance of GNN trained on such synthetically generated dataset. Fact number one is that open datasets are small. This is obviously true for almost all domains of data for deep learning. For graphs, it is taken to extremum. Going, for example, to OGB that has a nice suite of graphs for different GNNs tasks, you will find that what is called large there are graphs of size 10 to the power of 8 of nodes and 10 to the power of 10 of edges. However, if one wants to solve real-world problems, then 10 to the power of 10 and higher nodes and 10 to the power of 12 or more edges is a minimum we are talking about. So we're at least 2 orders of magnitude higher than the datasets available there. Also, because we don't want to copy the amounts of data whilst sharing the datasets, but rather fit the generator on the one machine and then regenerate it on the another one. For this purpose, our ideal generator needs to be fast, where the velocity of generator is measured in generation speed expressed in edges per second. I won't speak about it today, but this speed requires GPU, obviously. That's why Nvidia is here. The generator should not be bounded by the RAM memory. There are machines of terabytes of RAM memory. Still, this amount is too small. And the third thing, the generated graphs needs to have similar characteristics to original ones. What is more, the task is rather defined as please generate similar graph but much bigger. Just a short reminder what a Kronecker Matrix Product is, because it will be helpful later. So if you multiply A times B Kronecker-wise, here is what you get. Simple, right? So if we know how multiplication works, we also know how Kronecker power works. Theta is in this example is 2 by 2, but the reasoning is generic. Let's think about it for a while. First of all, if theta is stochastic, then the Kronecker power of theta is stochastic as well. Nice. We can use it as a distribution we sample from. Second, we have a direct influence of the size of this distribution by setting the Kronecker power value. Thirdly, if theta is not square, so not 2 by 2, but n by m in general, then the Kronecker power of such matrix is also not square, but the shape changes exponentially. So now we can formulate the task of the generator. So if the graph that we want to mimic, graph G, is represented by adjacency matrix A, then we'll try to find a similar graph, G hat, that is represented by A hat, that contains E, which E is a number of edges, E samples, and we will sample from distribution which is according to the Kronecker power of the seeding matrix data. Okay, that was abstract. Let's have a simple example. Okay, A hat is in the nth Kronecker power of theta, which is a 2 by 2 matrix of real numbers. In order to produce A hat, which is a kind of realization of distribution, we need to follow one of two ways. We either produce theta to the Kronecker power n that has 2 to the power of n nodes and sample e edges from it, or we sample each of the edge in n steps where n is a Kronecker power. Both of those ways are equivalent, but the second one seems better due to the space complexity. We don't have to keep theta to the Kronecker power n in memory. So if a hat is 8 by 8, theta was 2 by 2, and therefore n is 3, then if we randomly select B, A, and D from the theta seeding matrix, meaning that we end up introducing an edge between node number 1 and node number 5, naming convention starts from 0, then we first deselect the top right corner of this matrix, then the top left one of the selected one, and then the bottom right, producing an edge between the mentioned before nodes. We know technically how process of generating edges works, which is sampled from distribution that we produced based on the Kronecker matrix product. But let's get back to our original task, which was to produce a similar graph. What does the similarity mean here? Okay, here we need to take the perspective of a graph tasks we are going to solve based on the synthetically generated graph. And there are two ways how I see it. The first one is that G and G hat are similar, obviously if A and A hat are similar. That is, A is almost the same as A hat. So A minus A hat, a norm of that should be very small. That means that we care about the permutation of nodes. This is the first view on this. The second one is that we don't care about the construction A and A hat. They can be different. The nodes can be permuted, but only some of the graph characteristics are preserved during the generation, and we'll compare those characteristics to state the similarity of the graph. Whilst the first approach is more natural here, seems more natural, it has one huge disadvantage. We will not be able to compare two different graphs, meaning the graphs of different sizes. And we stated at the beginning that we want to solve that kind of problem as well. Having that in mind, let's take the perspective of how to find parameters of the generator. If theta is 2 by 2, then it should be fairly simple to find the parameters. There are only 4 of them. Then we'll focus on analyzing degree distribution as the characteristics we want to compare between the graphs. So just a reminder, the degree distribution is what you see right now on the slide. It's this kind of plot where for each and every node degree k, we have a number of nodes ck having this degree. For most of world real graphs, the degree distributions follows the power law. So summarizing, we will say that two graphs are similar if their degree distribution is similar. Analyzing the problem of finding ABCD parameters of seeding matrix data, you'll be able to come to two main conclusions. The first one is that A hat, the adjacency matrix of G hat, might not be symmetrical, and this is because the graph can be directed. So there is an in-degree distribution we need to fit, but there is also an out-degree distribution, and we need to fit both of them to have the similar graph. The second one, very important, is that the in and out degree for each node is just a sum of edges coming out or coming in to this node. That is, it's a sum for each and every node of ones in the A hat. So if it's a sum, then it has to do something with the binomial distribution. And actually, this is a binomial cascade, where the expected value of ck is the expected value of this cascade. Why this is so important? Because we have a closed form solution. That's very, very cool, because we know how to deal with that. We know how to fit that kind of cascade, especially that the parameters of ck out, so the degree distribution for each and every k for out degree distribution, and ck in has a single parameter, which is p or q. This binomial cascade equations might look scary, but they are not scary at all if you think about it for a while. The nice fact about having this particular closed form solution is that, first of all, in real graph, the distinct k's are around log 2 of n, where n is the number of nodes in the graph, which is cool. The second thing, the complexity of the sum calculation is small n, and the small n is just a ceiling of log 2n. And also, if you look closer on these Newton's symbols, we can pre-compute it before doing any optimization, finding P and Q. Some of you might state that we have only 4 parameters. Why do we even need to fit it? We overcomplicate the problem introducing some binomial cascade equations that we need to optimize for P and Q. If you think this way, then you will end up with something like this. So the blue curve is the degree distribution for the original graph, and the orange one is a randomly generated graph from the Kronecker matrix product without fitting. And this funny orange curve is not a surprise, because it's simply a binomial distribution curve. I didn't mention that, but obviously fitting is done by minimizing the difference of the true degree distribution of the real graph, so true CK, and the CK hat that we were given by the binomial cascade. So if the fitting is done, we end up in a situation like this. Oh, we did not expect that. What are those funny bumps? Careful mathematical analysis of the binomial cascade gives us justification, but it takes several plus equations to show it. So I will simply say that the theoretical model in a form of this binomial cascade, which is shown here as theorem 1 curve, is a good predictor of what is really happening when we realize the sampling from the Kronecker power. That is, the model provided before is correct, and we need to change a bit. How do we sample? So instead of sampling from the theta to the Kronecker power k, we'll sample from the Kronecker product of theta i's, where each theta I is a noisified version of theta. This noise needs to follow some particular distribution, but even with uniform noise, as in this picture, the results are really good, as the shape of the generated graph's degree distribution follows the power law, and the original and noisified one are almost ideally aligned. Okay, so we fitted the degree distribution quite well. What about the other characteristics of the graphs, especially the global stats, connectivity, transivity, and path stats? So if you'll take a closer look on the left-hand side of the slide in the table, you will find that almost all characteristics of the graphs are perfectly mirrored. This is a nice side effect of fitting the degree distribution. Obviously, I'm presenting results for a single realization, but if you'll check that approach on other graphs, you'll see the solution is consistently good. What can bother us here is that the graph that is generated is not strongly connected. But this situation is not that bad, because as you see in the line 16, almost all, 99.98% of the nodes are in the largest weakly connected component. So nearly everything, including the average degree, which is very similar in line number 3, or unidirected edges and directed edges, as well as the path stats, including the 90% effective diameter in line 20 that is almost perfectly aligned, and the number of open triangles that are in the same order of magnitude. So all this show that even though we fitted for a degree distribution only, the global statistics of the graph, connectivity, transivity, and path stats are well mirrored in the generated graph, which is cool. What about the other characteristics of the graph, especially including the spectral properties of the graph? So if you look on two most important ones, which is a singular value rank distribution, then the original and generated graph are also very similar. Also, if you look to the leading singular vector rank distribution, then the generated graph is almost identical as the original one. This means that the properties that are around clustering coefficients for the graph will also have good properties when comparing the generated graph, the synthetic one, and the original one. So up until now, we've been talking about the simplest possible graph, which is homogeneous in edges and homogeneous in nodes, maybe a graph that is directed. What other types of graphs can we encounter? So, for example, for non-directed and directed graph, we already know that our generator can fit that kind of graphs well. What about bipartite or n-partite? Simply, we need to explode the process of the generating into several stages so that whenever the graph is n-partite, we need to generate the adjacency matrix for each partite as the example in the bipartite graph. Obviously, if the bipartite graph or n-partite graph in general is non-directed, we only need to generate a single adjacency matrix and then transpose it in order to build a full adjacency matrix for the entire graph. In case of the directed n-partite graph, we need to generate the adjacency matrix for each and every particular partite of the graph. It seems that we have a perfect generator, having in mind that generator itself is quite easy. There is a very effective and efficient procedure of fitting it, and we get a very good degree distribution mirroring between the original graph and then the synthetic one, on top of which all the characteristics of the graphs, including the general stats, the transivity, connectivity, and others, they are quite well aligned between the original graphs and the synthetically generated ones. However, there are some caveats. Look on this example. This is a movie lens graph which does not follow the power law for degree distribution. Movie lens will obviously be a bipartite graph, heterogeneous in nodes. We have users and items obviously, but homogeneous in edges. Edges means that the user rated particular movie. The only one reason why it does not follow the power law degree distribution is that the authors of the datasets filtered out users that have less than 20 interactions, leading to unnatural degree distribution, which can be seen in the bottom left plot, where obviously this is not a good log degree distribution. So basically, how can we deal with that kind of situation? So the only one way how we can solve it within the current way of thinking about the generator is that we need an access to original graph, so not a filtered one like the movie lens is, to fit the parameters for this original graph, and then filter out accordingly, meaning that the filtering procedure for the original and for the synthetic ones are the same. Okay, we know that the properties of synthetically generated graphs are very good. That is, we can mimic easily the characteristics of the original graph once the generator is fitted. Let's now answer the primary question that we had. Does this bring any value to simulating the performance of GNN? Okay. On this slide, you have 3 plots. All of them contain data from training simple graph attention network. The architecture of GNN is not that important here because I will tell you in a while that what we found out here, it holds for all the GNN architectures. The GNN was trained with edge data loader. That is, each and every batch of data, and the batch size is 1000 edges, we have created a subgraph based on those 1000 edges, but by taking all neighborhood nodes within k hops from nodes that are at the ends of those edges in the batch. So that's why we have 3 different hops values, 1, 5, and 10. And this is why we have 3 different plots here. We have measured the same GNN, but we trained it on 3 different data sets. The original one, so the original bipartite graph, the fitted one, and so that created as a synthetically generated graph, which is depicted here as SKG, Stochastic Kronecker Graph, and the third one, the random one, which is generated with Erdős Rényi model. And that's why there are 3 box plots on each and every plot. Remember, every single point of the distribution that we present is an observation, and this observation is a block size for the particular batch whilst doing the training. You may ask, why block size and not the throughput, for example, in samples per second? Well, what I wanted to measure is I wanted to measure something to be agnostic in terms of the GNN architecture, and block size describes well the problem size that we are dealing, because since the time complexity of further calculation with GNN strictly depends on the input data size, which in terms of the edge data loader is simply a block size. So a block size is a good proxy to state how long we will need to calculate all the things we need within particular step of GNN training. Okay, so we can see multiple things here on this slide. The first one is that there are outliers. Is this good? Well, it's not good and not bad. Those outliers are just last batches which do not contain the full batch size, that is 1000 edges. The second and more important thing is that SKG, so the synthetically generated graph with fitting, and the original ones are very close in distributional sense to each other, whilst the Erdős Rényi is far away. This especially holds for hops equals 1, which is not surprising because the larger the hops is, the bigger the subgraph is. So if the hops is large enough, then without found out, we will be able to sample the entire graph within one single batch, which obviously makes no sense. And smaller hops is actually the situation that we'll encounter in the bigger graphs. If this result can be generalized to other GNN architectures, and I believe it can be, and for other GNN sampling mechanisms, for example, the sampling mechanisms that are specific for graph property prediction or node classification, then we'll have an excellent tool to check the performance on extremely large problems and find bottlenecks in computational pipelines for problems we don't have open data sets, but we know that the customer problem size is of this ON. To summarize and conclude, so if you want to measure GNN performance, or in general performance of any task that we can do on graphs on the world scale problems, then we need to generate those graphs synthetically, simply because there is no access to the open source data sets of this size. Secondly, not every graph that is generated using the Kronecker Matrix product is a good graph for mimicking original graph properties, and our demand is to have this mimicking of those characteristics. If one wants to mimic the characteristics, then the only one way is to feed the generator, not to take their parameters randomly, and obviously to noisify it. Universal generator should be able to generate any type of graph. In general, it should generate n-partite graphs, that is heterogeneous in nodes and heterogeneous in edges, and we showed that even though the plain vanilla Kronecker based stochastic generator cannot do that, but we can combine the results of different generators to find a proper adjacency matrix that represents this kind of complicated graphs. For word size problems, we need a generator that is trivially parallelizable. Why is that? Because at the end, we will need to generate 10 to the power of 12 nodes, 10 to the power of 14 edges at least. So having a generation speed of million of edges per second is simply not enough. If the results that we have presented today can be generalized to other GNN architectures, and we don't see the point why it shouldn't be so, but obviously we need some experiments for that. And for other sampling and data loading mechanisms that are specific to others GNN tasks, others than the recommendation system or link prediction in general, then the generator that we talked about today satisfies all conditions to be almost a perfect generator. Okay.
Thank you very much, Piotr, for an interesting talk, and thank you for joining me here live. We have some talks from the audience, and Joanna asks if there are any other common graph generators, and if there are, what makes this one different from the others?
All right, that's a very good question. So just to name two silos in which those generators live. So the first ones are like simple in terms of form, but efficient in terms of the results, in terms of mimicking the graph characteristics. So in this first silos, you will have models like Erdős, Rényi, or Barbashi Albert, or the one that I presented right now, which is a generalization of all the generators that you can capture under the hood of Stochastic Kronecker Matrix based. And in the second silos, you will have a much more complicated model-wise generators, like some deep learning generators. But the second silos is cool from the perspective of the data scientist and the development. However, if we are targeting the performance here, and this is one of the reasons why we went through the path of having a kind of easy to understand generator but a performant one, then you will see that the speed of generation, which is 10 to the power of 8 edges per second, you won't be able to achieve using any much more complicated generative model, whether this is some simple machine learning based generative model or deep learning. So if you want to have the speed, you need to go towards the Kronecker based generators. But on the other hand, the results that we showed today they show simply that you're not losing anything in terms of the quality of the generator, because all the characteristics of the graphs are well mimicked, and what is more, they serve the main purpose, which is the mimicking the performance of the GNNs. Okay, hopefully this answers Anna's question.
Thank you. And there is another question from Arthur. Have you measured the performance difference between generating directed and non-directed graphs?
Basically there will be no difference in the performance. I understand here a performance as a throughput measurements, not the performance in terms of the quality, because data scientists tend to understand different things under the hood of the performance. So from the perspective of the throughput, so numbers of edges per second that we can generate, there will be no difference between the directed and non-directed graph. There will be a difference between non-partite and n-partite graphs then, because we need to, as I mentioned on the presentation, we need to provide this generator in terms of doing the generations in stages, generating one partite at a time. And this has to be done in series. It cannot be parallelizable very easily. In terms of the quality, there is no loss of the quality, but by saying quality, I'm saying about mimicking the characteristics of the graphs, the path stats, the global stats, the connectivity, transivity, and so on and so forth. So you would not encounter any drop in the quality of the generated graph when comparing the directed one to the non-directed one.
Thank you very much for your comprehensive answers. And thank you again for joining us today during the the conference.